Welcome back, learners. You know, in the previous lecture, we have completed the design of the footings, and even we have given the reinforcement details as well as the footing groupings, everything we have learnt. Now, in this video, that is session, let us start the design of the columns. Now, when we want to have the design of the columns, the first and the foremost step is you should know the values to which the column has to be designed. Like how you got the support reactions, in order to design the footing. In the same manner, you should have the loads or the moments for which the column is to be designed. That how to get it from the ETABS software, that we will see in the next session. But in this video, let us try to prepare the Excel sheet for the columns design. Now, when it comes to the column design, so we have mainly three types of column designs. And before that, I would like to make it very clear that in the footings also we have learnt concentric isolated footing, because in this problem all the footings whatever we have done is all of concentric isolated footings. So when we take up the next problem, that there may be a chances of having the eccentric isolated footing, definitely we will take the problem in such a way that eccentric isolated footing will come. In that case, so I'll explain how to develop the footing design sheet for the eccentric isolated footing, right? And next problem we may have the problem of facing the combined footing. So that time let us take the problem of having the designing the Excel sheet for the combined footing. Like that, by the time you complete all the problems, you will be learning all types of footings. Now, when it comes to the column also, usually we have majorly three types of columns design. So we will design the columns only for the axial load. Okay, we will design the column only for the axial load, and we call such kind of columns as axially loaded column. Okay, axially loaded column. That means they are subjected to only axial loads, so they are axially loaded columns. And the second type is along with the axial load, they will be having movement in the one direction. So we are going to design for that, and we call that as uniaxially loaded columns or single moment axially loaded columns. And one more is you are having axial load, along with that you will be having two moments. So one in the one plane, another one in the another plane. We call them as biaxial loaded columns. Okay, so these are the three types of columns. But when it comes to the practical designs of the columns, usually you won't find any columns which is axially loaded. That means having only axial load, other than axial load, no other loads will be present, only axial loads will be present. So nowhere you will find such kind of columns, right? So you find only at least uniaxially loaded, and most of the columns will be biaxially loaded columns. So therefore in this session, so I will be explaining you about the design of uniaxially loaded column, and in the next session you will be having we will learn how to design the biaxially loaded column. And you should know that how to identify whether the column is an uniaxially loaded column or a biaxially loaded column. Okay, so now let us learn this is the design procedure that we are supposed to follow for the uniaxially loaded column. The same thing let us try to design in the Excel sheet also. So therefore let me open one Excel sheet, and let me give the first as this column number. Okay, so this is the column numbers. So this is an input value, and let us keep it in the middle. Let us increase the size, and let us give some coloring. This will be my column numbers. Now according to this, the first step is that you should know is what should be the grade of concrete that you use for the column, that is FCK. it is an input value which is given in Newton per mm square. So therefore let me give grade of concrete for the column, right? So this will be the grade of concrete for the column, and that is FCK, which is given in Newton per mm square. And since it is an input value, let us make this to green color. Green color represents the input value that we are supposed to give. Then next you have the shorter dimension of the column, which is represented as small b. That is also an input value which will be given in mm. Okay, so shorter dimension of the column, right? So that will be in mm, right? This is also an input value, so therefore let us give like this. Then after that, even you need longer dimension of the column, which is given in capital D. That is also an input value, that will be in mm. I can directly bring this here, making this as longer dimension of the column, that is also will be in mm. Okay, yes, green. So then after that, shorter dimension, longer dimension. Next is axial load on the column. That is also an input value. Usually we give it in kilonewton. That is an axial load on the column, right? Axial load on the column, which will be given in kilonewton. Okay, which will be given in kilonewton. Okay, yes, right, axial load on the column. Then moment at the base of the column. So as I already told, we are designing it for an uniaxially loaded column. That means axial load with one moment. So therefore I am just going to give moment at the base of the column. If there are two moments, then we have to specify along which direction, whether x or y. Okay, so therefore it is just the moment at the base of the column. Moment at the base of the column, which will be given in kilonewton meter. Okay, which will be given in kilonewton meter. So that is moment at the base of the column. So these are all the input values. Then the effective cover to the column. As per IS 456-2000, for the footing, the minimum cover that should be provided, it is an 50 mm. Whereas for the column, the minimum cover should be provided is 40 mm. But there is a clause, in case if you are designing the column for a very small dimension of less than 200 mm. Again I will repeat, if you are designing the column for a very small dimensions of less than 200 mm, then you can provide a cover of 20 mm. In case if any one of the dimension, whether longer dimension or shorter dimension, any one of the dimension, if it is more than 200 mm, then you have to minimum provide the cover of 40 mm. This is as per IS 456. So therefore we are supposed to provide the effective cover to the column of input value, which will be in mm. Effective cover to the column, which will be in mm. Effective cover to the column, which will be in mm. So if you want, we can give the signs as FCK. Okay, I can write it as FCK. Then shorter dimension I can write it as B, longer dimension I can write it as capital D. Then axial load I can write it as PU. Then moment I can write it as MU. Then effective cover I can write it as small d dash. Okay, yes. So then after that you are supposed to find out a value called as d dash by d. Okay, supposed to find out the value called as d dash by d, right? So we'll write this, it is d dash divided by capital D. Okay, so there is no symbol for that and there is no unit because everything will get cancelled. Okay, yes. So let us try to give some values here, so that the grade of concrete, let us give 20. Okay, let us give the grade of concrete 20. Then let us give the shorter dimension as 230 because it is in mm, 230, and let us give longer dimension as 460. Okay, so let us give 460. Then let us give axial load in kilonewton as 770. So let us give 700 just for the sake of. Then moment at the column they have given 10. So we will give 10 and I will explain you where we will get these values. Then effective cover, as I already told, 40 mm. Then I am supposed to calculate d dash by d, which is equal to, so d dash is this divided by this d dash by d. So that will be your value of d dash by d. Okay, that will be your value of d dash by d. Once you get the value of d dash by d, then we are using a chart called SP16 chart. So in the SP16 chart, so we have three sets of charts. The first set of charts will give you the percentage of steel required for the column when you are designing the column for only axial load. And the second set of charts will give you the values for the percentage of steel when you are designing the column for the axial load and uniaxial moment. That is this one. And another set of charts will give you the percentage of steel when you are designing the given column. Okay, when you are designing the given column for the axial load and two moments, that is what you call biaxial moments, right? But in order to do that, so I'll just show you that where the charts are. Okay, I'll just show you the charts, right? Yes. Okay, so let us go to the chart of 36 something. Let's see. Yes, you can see here. So from here, the chart number 27, so your charts represents the percentage of steel for the columns with uniaxial, that is axial load with one bending. Okay, now your charts will be selected based on the different criteria. The first criteria is based on whether you are using the rectangular column or you are using the circular column. The charts for the rectangular column is different, the charts for the circular column is different. Okay, the charts for the rectangular column is different, the charts for the circular column is different, right? Yes. Now this charts represents for the rectangular column, that is one criteria. Second criteria, again the charts in the rectangular column or in the circular column, you will be having different charts again for the reinforcement that you are going to provide on all the four sides of the column, or reinforcement you are going to provide on any two opposite sides of the column. Okay, for example, now if you take this, and that is second criteria, that is whether you are going to provide reinforcement on all four sides or you are going to provide only on two sides. Then third criteria is based on your grade of steel that you are going to use, whether you are going to use F5 is equal to 250 or 410 or 500. That is the third criteria. And fourth criteria is based on your d dash by d value, right? Now you can see this chart is for FV 250, d dash by d 0.05 and rectangular column with reinforcement on two sides. Same 250, but d dash by d becomes 0.1 and this with rectangular two sides. Then d dash by d changes. So these are all for the rectangular columns, f of y 250, reinforcement on two sides and different values of d dash by d. Okay, now this is for Fe415, like that for the different values of d dash by d. Okay, Fe415. Then next you have Fe500 with rectangular column, reinforcement on all two sides, right? That is for 500 with different d dash by d values, right? Yes. So then you can see this charts will again start with Fi250 for the different values of d dash by d with the rectangular columns, but reinforcements provided on four sides, right? So these are all for the Fe250 with reinforcement four sides. Then Fe415 with reinforcement four sides, right? Then similarly Fe500 with reinforcement four sides, right? So now you can see again the same procedure will start, but with for the circular column. But in circular column you cannot expect us to have the reinforcement four sides or two sides. It will be provided out and throughout the circle, right? In this way, based on the dimension, that is whether it is rectangle or circle, based on the reinforcement whether we are providing two sides or four sides, and based on the grade of steel, that is Fi250, 415 or 500, and based on d dash by d value, we have to choose this. And you can see all charts will be having two values. One will be mu by FCK BD square, another one will be Pu by FCK BD. Okay, one will be mu by FCK BD square, another one will be Pu by FCK BD. So based on these two values, we will get the value of P by FCK. That P represents the percentage of steel. You will get P by FCK, right? Yes. So now therefore after d dash by d value, my next step is I am supposed to find out mu by FCK BD square value, right? So I am supposed to find out mu by, I can put it in the bracket, FCK into B into D into D. Okay, mu by FCK BD square. Then next you have, this is not yes, so this will be in the black color this will be with the black color because this is an automatic value generated. So this is also black color, automatic value generated. Next you have Pu by again FCK into B into D, Pu by FCK BD. So these are the two values. So again, so no any symbols or anything for this. So directly it is the value, right? Yes. So when you are doing this, so I can give that first I'll open two brackets. So first will be mu. So this will be in kilonewton meter. I am supposed to convert it to Newton mm because my B value and D value they are in mm. Therefore what I'll do, I'll consider this, then I'll multiply this by this much value divided by, again I'll open, so I have FCK 20 into I have B this one into I have D 2 times, right? Yes. Then I'll close this, I'll give enter. So this is my mu by FCK BD square. Then similarly next you have, it is Pu by FCK BD square. So therefore I have to open two brackets. First this is in kilonewton, I have to convert it into the Newton into 1000, right? Then divided by, I'll again open the bracket, then I'll go FCK into B into D, right? Yes. So I'll close the bracket, enter. So this is my Pu by FCK BD, right? So once you get mu by FCK BD, then Pu by FCK BD, then what you are supposed to do, you are supposed to get the P by FCK value, that is an input value obtained from the chart between 27 to 50 of SP16. Why 27 to 50? It is a rectangular columns with different grades of steel, right? So these two. Then next you have P by FCK value, it is an input value, right? P by FCK value, it is an input value I am supposed to give, right? P by FCK value I am supposed to give, right? Okay. Yes. So now let us go to the table. So let us go to the rectangular columns going to provide on all the four sides with FE415, right? Yes, this is 250. So this is the rectangular column with F of I is equal to 415 with reinforcement on four sides. I have to check D dash by D value. You can see here my D dash by D value is 0.08. So 0.08 is not there, means I have to round it off to the, I have to come back to the previous value, that is I can come to 0.05. You can see 0.05 is there, I can come to 0.05. Okay, D is the longer direction, B is the shorter direction, right? 0.05. Now in that, what is my MU by FCKBD? My MU by FCKBD is again 0.01. Then PU by FCKBD is 0.33, right? So now 0.1, okay, 0.01, 2, 3, 4, 5, 6, 7, 8, 9, 0.1. So therefore 0.01, or I can go to 0.02. So here I am supposed to go, right? And what is my MU by FCKBD? It is 0.33, right? So this is 3, 2. So I can get somewhere 0.3 in the middle. Therefore I can go and I can come here. But you can see that there is no any values here, right? There is no any values. So therefore, so 0.33, I will directly go to the first column. So let us go, it is 0. So let us go to this, which is 0.02, okay, which is 0.02, right? 0.02. So this will be my value 0.02, which is an input value given in, right? It is an input value, right? Okay. .02. So once you get 0.02, then you should get the next step, percentage of steel. How? You multiply that by P by FCK value into FCK, you will get percentage of steel, right? So therefore I can give percentage of steel, which will be given as P, right? Which will be given as P, right? So it is P, right? So it will be in percentage, right? So therefore what I am supposed to do? I am supposed to multiply this by FCK. When you do that, you are getting value 0.4, right? But as per IS 456-2000, as per IS 456-2000, so when you want to give the reinforcement to the column, okay, when you want to give reinforcement to the column, okay, when you want to give reinforcement to the column, the minimum percentage of reinforcement that you are supposed to give for the column is 0.8%, okay. The minimum percentage of reinforcement that you are supposed to give for the column is 0.8%, whereas the maximum percentage of column that you can give to the column is 4 to 6%. You can give up to 6%, but keep it in mind that even 6% is practically difficult. Because why it is difficult is, you can provide the reinforcement, but after pouring the concrete, while doing the vibration, that is compaction, so your compaction will not be done properly. So therefore it is not good, okay. So therefore usually we go up to the maximum percentage of 4%, but minimum percentage you are supposed to give 0.8. If you are getting any value less than 0.8, then you are supposed to consider the percentage of steel as 0.8. Therefore let us create one more row, that is actual percentage of steel provided, okay. So that way let me give as P only, this let us make it as P dash, okay. This is P and this will be percentage, and okay, so this is also an input value, so this is also an input value, let us give this as 0.8, okay. So these two are the input values only, right? Okay, yes. So after this, so once actual percentage of steel provided if you got, the next step is you are supposed to calculate area of the steel, that is percentage of steel by 100 into the longer dimension into the shorter dimension, right? So therefore I can give total area of steel is equal to, I can write it as AST, okay, which will be in mm square, right? So that will give you the value. So it will be, it is 0.8 into this divided by 100, right? So that will give you the total area of the steel, it will be in the mm square, right? So the next you are supposed to find out the diameter of the rod that you are going to use for the given, this will be in black color, okay, yes. So this is area, then you are supposed to give diameter of the reinforcement, diameter of the reinforcement. So that let us give in form of phi. So insert symbols, right, phi, right, okay. So that will be in mm, and let us give the diameter as 16, okay. So that will be in the green color only because it is an input value, right? Then area of one reinforcement, okay. I can write it as small AST, which will be in mm square, okay, which will be in mm square. So that will be equal to, so pi by 4 d square, that is 3.142 into 16 into 16, okay, 16 into 16 divided by 4, right? So that will be the area of one reinforcement, right? You can see here area of the rod, then you will get total number of rods, right? You will get the total number of rods, total number of rods, total number of rods, okay. So this will be in the this is not in the green color, right, yes, total number of rods, that is also will be in the not in the green color. So that will be equal to, so you can get it as total number of rods will be area of the one rod by the total area of the steel, right, into 1000, yes or no, yes. Sorry, total number of rods, just give me a minute, it will be yeah, so it will be this total area divided by this, that will give you total number of rods. Usually you will get it in numbers, right, usually you will get it in numbers. So now we are always supposed to provide the reinforcement in the columns in the even numbers, and you know, as per IS 456, if you are using a square or a rectangular column, your minimum number of rods that you are supposed to provide is 4, and if you are using a circular column, the minimum number of rods that you are supposed to provide is 6. And usually if it comes 4, 5 or like that, usually we round it off to the next higher even number, okay. You are getting 4.2 means we will go to 6 because 5 numbers cannot be provided equally on the any column, therefore we will go to 6. So therefore I can give one int as final number of rods provide it. Okay, so that will be an input value which is 6. So therefore this, let us make it as green color, because you know it is an input value. Okay, yes. So once this is done, then next you are supposed to provide the lateral tie spacing. Okay, so the lateral tie spacing I am supposed to provide. So that, let us make one small column like this. Okay, let us make this column. So merge. So I can give lateral reinforcement. Okay, so yes, so let us make this bold and some color, right? Yes, lateral reinforcement. So when it comes to lateral reinforcement, the first step is, what is the diameter of the rod that you are using for the lateral reinforcement. Okay, so the diameter of rod for lateral ties, right? So that will be 5, and that will be, you know, mm. Okay, and this is an input value, so therefore we will be giving it in the green color. So let us give that I am using 10 mm lateral ties, right? So once you decide that, you are supposed to find out the spacing, okay, which depends on these 4 values. So I am supposed to find out the spacing of lateral ties. Okay, spacing of the lateral ties. So that will be decided based on the 4 criteria. So the first will be, right, so the first criteria that I am going to use, least lateral dimension, right? So that will be least lateral dimension. Okay, so that will be the first criteria, that is least lateral dimension, right? So that will be in mm only. So I am supposed to choose the least lateral dimension. So definitely out of these two, the shorter dimension will be the least lateral dimension. I'll give you this. Then the next will be 16 times the dia of the main rod, 16 times the diameter of the main reinforcement. Okay, the second will be, right, the second will be 16 times the diameter, 16 times the diameter of the main reinforcement, right? So 16 times the diameter of the main reinforcement, right? That will also be in mm, but this will be 16 into, right? So what is the diameter of the reinforcement? This one, right? So that will be the second case. Okay, yes, that will be the second case, right? So then third one will be 48 times the dia of the lateral ties, right? So the third one will be 48 times diameter of the lateral ties. So that will also be in mm, but that will be 48 into this, which will give you 480, 48 times the diameter of the lateral ties. Then last one will be, it will be always 300 mm. Okay, it will always be 300 mm. 300, so I am going to give 300 here, right? Yes, that will be in mm. Out of these, whichever you are supposed to choose is supposed to choose the least dimension of these 4. Okay, so least dimension, therefore I can give the spacing the spacing of lateral ties will be in mm. It will be, you can give minimum, you can give minimum of this, comma this, comma this, comma this. So this is the minimum of this. When you enter, the minimum of this is 230 mm, and again the 230 mm usually we will not keep it as it is, we will round off to the next lowest number. Okay, we will round off to the next lowest number. Okay, so therefore the final spacing of the lateral ties, okay, final spacing of lateral ties which will be given in mm will be 200, right. So this is an input value, right. So in this way you are supposed to design an uniaxially loaded column, right. So let us see what is the next procedure in the next video. Thank you, learners.